looking at electronegativity and intermolecular forces. So first, we need a good definition of what electronegativity is. And electronegativity is an atom's pull, or the attraction for the electrons in a chemical bond. It's pretty much how badly does that atom want the electrons in that bond. What's its pull? What's its strength? What's its desire? How strong of an attachment does that atom have for the electrons in a bond? When we look at the periodic table, there's going to be some trends that we're going to be able to see in the periodic table. Electronegativity will increase as you move up on the periodic table, and also as you move to the right. So as you're moving up, it is increasing. As you're moving to the right, it is increasing. Kind of an easy way to remember that is that fluorine is the most electronegative element, and it lives in the top right-hand portion of the periodic table. Now you may be looking at a periodic table right now, and you say, well, there's some elements to the right of fluorine, or to the above fluorine. Well, those are the noble gases. Things like neon and some of the other noble gases, even though they're to the right of fluorine, they don't form bonds with other elements. So if you're not forming a bond with another element, you don't really have an electronegativity value. So those noble gases aren't going to really count for us. And what we want to do in this video is re-explore some of the things we just talked about with bonding, but putting it in context with what we just talked about with electronegativity, so we can add a little bit more details for what we've already discussed involving bonding. And we can do that through using electronegativity. So first, just a quick look at the periodic table to kind of go through those trends. Remember that as you go up on the periodic table, electronegativity is increasing, and as you go to the right, electronegativity is also increasing. We talked about fluorine being the most electronegative element. It's in that top right. Remember, those things to the right of fluorine, the noble gases in 8A, they're not forming bonds with anything, so if they're not forming bonds, they don't really have a true electronegativity value. So you can look at pairs of elements on the periodic table and then use this trend to figure out which one's more electronegative. So if we looked at silicon and above it carbon, if we looked at both of those, we could say that carbon is more electronegative than the silicon because carbon is above silicon on the periodic table. Likewise, we can use the left and right trends as well to kind of pick some things out. All the way on the left-hand side, if I pick out rubidium on the periodic table circled in blue on the left, and then I compare that to iodine all the way on the right, well, iodine is to the right of rubidium. That means it's going to be more electronegative. In the first case that we want to consider is we want to look at what happens when we have two elements with a large difference in electronegativity values. So this is something, if you think back to the trends we just talked about, this is going to occur whenever you have a metal bonded to a nonmetal. We would recognize the nonmetals as having a very large electronegativity, and the metals having a very small, much lower electronegativity. So the difference between those would be pretty great. So we'd have a large difference. We know previously from doing the nomenclature that whenever we have a metal and a nonmetal, we would be looking at an ionic bond. Well, our most basic ionic compound we can think of, NaCl, we know we're dealing with ionic compounds. So we're going to have sodium ions and we're going to have chloride ions. Because of this large difference in electronegativity values, these two elements are incapable of sharing electrons. If you think back to the Lewis structures that we've also done, we kind of showed elements sharing electrons represented by the lines that bond between the elements. Well, for sodium and chlorine, because that electronegativity difference is so great, they're incapable of sharing. These are not going to be able to share any electrons. And we can kind of think about what happens. Chlorine is very electronegative. It's pretty close to fluorine on the periodic table. It's in the upper right-hand part. It's very, very electronegative. It really wants the electrons. It has a strong pull for those electrons. Sodium, all the way on the left-hand side of the periodic table, is not very electronegative at all. It doesn't really want the electrons that badly because chlorine wants them so much and sodium doesn't want them at all. Chlorine is just going to take the electrons. Sodium's not electronegative enough to put up a fight. So in the struggle for the electrons, the chlorine really wants the electrons. Sodium doesn't really care so much about the electrons. So sodium can't put up a fight. Chlorine is just going to grab the electrons. Sodium's going to give it away, resulting in those ionic compounds. So for nomenclature, we talked about metals and nonmetals having ionic bonds. And the reason they have ionic bonds is because of this big difference in electronegativity values. For our second case, we want to look at the complete opposite extreme. This is when you would have no difference in electronegativity values. So here we would be looking at things like two nonmetals with the exact same electronegativity value. And the easiest way to think about an example of this would be two of the same element. If you had two atoms of the same element trying to bond together, well, each atom of that element would have the same electronegativity as the other atom of that same element. Now we know previously from the nomenclature we talked about that two nonmetals are going to form a covalent bond. So let's look at what happens in this no difference in electronegativity values. An example of this would be something like chlorine gas, Cl2. Here we have chlorine bonded to another chlorine. Well, being they're the same element, each chlorine atom would have the same electronegativity as the other chlorine atom. So we know the electrons are being shared, but we can go a step farther. Because of the exact same electronegativity value, the electrons are not only shared, but they're being shared completely equally. These electrons are being shared completely equally. What that's going to give rise to is what we call a nonpolar covalent bond. And this nonpolar covalent bond, because the electrons are equally distributed, there's no charge buildup. There's no different regions. It's very uniform, this molecule, in terms of what's happening with the electrons. We call that a nonpolar covalent bond. So in the first two cases, we looked at the extreme cases, kind of the bookends. One where we have a big difference in electronegativity value in the first case, and then we just looked at when we had no difference in electronegativity value. Now we kind of want to look in that in-between land. And that in-between land is what we're looking at for this third case. Here we have two elements with a small difference in electronegativity. You're going to run into this situation when you have two different nonmetals. So a good example of that would be something like bromine bonded to chlorine. So these are both nonmetals. So we recognize from the nomenclature, whenever we have two nonmetals bonded together, we're going to get a covalent bond. But this is going to be a special type of covalent bond. It's going to be a little bit different than the covalent bond we looked at when we just had Cl bonded to another Cl. So let's look at what happens here. So first off, for BrCl, if we look at bromine and chlorine on the periodic table, chlorine is above bromine on the periodic table. That means chlorine is a little bit more electronegative than bromine, but they're close. There's not a big difference. We're not in the same situation when we had sodium and chlorine. When we had sodium and chlorine, we had a huge difference in electronegativity values. Chlorine would just take the electrons from sodium. That's not what we have here. So chlorine is not so electronegative compared to bromine that it will just take those electrons and we'd get an ionic compound. The difference isn't big enough. Chlorine isn't electronegative enough compared to bromine to just outright take the electrons. But chlorine is slightly more electronegative than bromine. So what that also means is we can't be in the situation we saw in the previous example where these electrons were equally shared, because chlorine does want the electrons more than the bromine. So they also can't be equally shared. So we kind of have a new situation here. And this new situation is what we call a polar covalent bond. This is this idea of an unequal sharing of electrons. The electrons are being shared still a covalent bond, but they're not being shared equally. Kind of put this in a non-chemistry context is if you think back to when you were a child. If you have a sibling, you're probably familiar with this idea of unequal sharing. Your parents may have told you or your sibling that you needed to share. Well, what they had in mind was completely equal sharing. But we all know that that's probably not the way it actually occurred. Whichever sibling was older, bigger, more aggressive, just wanted it more, kind of got the toy more often than the other sibling did. It wasn't permanently theirs, otherwise that would create trouble with mom and dad again, but it probably wasn't completely equal either. There was some level of unequal sharing happening. And that's what we're looking at here for bromine and chlorine. So the way we represent this is, you can see the bond between bromine and chlorine. And the strange looking symbols you see next to the bromine and the chlorine are the Greek letter delta. And whenever you see that lowercase Greek letter delta in chemistry, it's chemistry shorthand for partial. So on the bromine, you see delta plus. That means, we'll highlight that in green, that delta plus, that means bromine has a partial positive charge. That doesn't mean it's ionic, it just means there's a little bit of charge buildup. On the other side, chlorine has that delta minus, that partial negative charge. So we see bromine coming in with a partial positive and chlorine with a partial negative charge. This is just a tiny, tiny, tiny charge buildup that occurs between here. These aren't ions. All this means is a partial charge buildup. Because the chlorine wants them a little bit more than the bromine, the electrons spend a little bit more time, slightly more time, closer to the chlorine than they will the bromine. And if we think about electrons, we remember that electrons are negatively charged. So if these negatively charged electrons spend a little bit more time closer to the chlorine than they do the bromine, well, then the chlorine is going to have that partial negative charge, and the bromine will have that partial positive charge. What we also sometimes do is draw what's called a dipole moment. And that's what you see on the bottom line. And what this is this is an arrow. And that arrow always points towards a more electronegative element. It's kind of like showing where are the electrons being pulled to. And then what you'll also notice is on the other side of the arrow, kind of using that red arrow now to point it, you kind of see that hash mark, that hatch mark. Well, that hatch mark kind of represents a partial positive charge on the other end, because in this example, the electrons are being pulled to the right. That means away from where the arrow is pointing. That's going to have that partial positive charge. You can see it kind of looks like a partial positive, kind of looks like a plus sign. That's kind of a symbolic way of representing this dipole moment. So we call this type of bond a polar covalent bond because there's two distinct regions on the molecule, two distinct poles on the molecule. So what we want to talk really briefly about is this idea of intermolecular forces. And for intermolecular forces, these are forces that exist between molecules. So far we've talked about what's happened within a molecule. This is what's happening between molecules. And what happens between molecules depends upon what's happening within a molecule. So intra means within, inter means between two molecules. And it should probably come as no surprise what happens within a molecule, intra, is going to affect what happens between molecules, inter. And to kind of give you a non-chemistry example of, how this kind of works is this is a little bit similar to how you might talk about your relationships. Your relationships are interpersonal between you and another person. But we know that what's happening within us, our mood, whether we're happy, sad, frustrated, what's happening internally to us, intra, can affect our relationships with others. Same thing's happening with the molecules. What's happening within a molecule is going to affect what is able to happen between molecules. So intermolecular forces are important because they play an important role in many of the physical properties of a compound, such as melting point and boiling point. The stronger the intermolecular forces are, the higher the melting point and the boiling points are. And that's because it would require more energy in order to disrupt those stronger forces in order to go from solid to liquid as you melt, or from liquid to gas as you boil something. We have 4 different types of intermolecular forces that we want to talk about. I want to talk about ionic, hydrogen bonding, dipole-dipole, and dispersion forces. And we've kind of ordered these from strongest to weakest. Ionic ends up being the strongest, and dispersion ends up being the weakest. So we just want to look at some examples of these different types of intermolecular forces. First one, our strongest intermolecular force is the ionic intermolecular force. And what happens is we have a strong attractive force between fully positive and fully negatively charged ions. And this is one of the reasons why our ionic compounds typically have very high melting points and very high boiling points, because they have this very, very strong intermolecular force. Now, we've kind of seen this ionic force when we've just been looking at, two ions. If we've just been looking at, like before, a sodium ion and a chloride ion, we've talked about that strong attraction between those individual ions. But now, intermolecularly, we're looking at a whole network of multiple positives and multiple negatively charged ions. So in the picture on the left, what you're looking at is kind of a two-dimensional display of this. We just wouldn't be looking at one positive ion and one negative ion. We'd be looking at a multitude of positive and a multitude of negative ions. And notice how each positive ion is surrounded by negative ions. Each negative ion is surrounded by positive ions. This is going to form a very strong intermolecular force. On the right-hand part of the screen, you see a kind of three-dimensional depiction of this, because it's not just in 2 dimensions, it's really in 3 dimensions. So these strong intermolecular forces is what gives you those high melting points and boiling points for your ionic compounds. So even though hydrogen bonding came next in terms of the next strongest one, we need to do dipole-dipole first because hydrogen bonding is kind of a special case of dipole-dipole. So we want to understand what's happening with dipole-dipole before we tackle hydrogen bonding. For dipole-dipole, we want to associate this with whenever you see polar molecules. And here, the partially positive end of one molecule is attracted to the partially negative end of a neighboring molecule. In ICL, so iodine bonded to chlorine, the chlorine is partially negative and the iodine is partially positive. This is very similar to the polar covalent example we did with bromine and chlorine. Here we saw bromine partially positive, chlorine partially negative. Same idea here with the iodine and the chlorine. Chlorine is above iodine on the periodic table. That means chlorine is going to be more electronegative than the iodine. So what you see, and again we see those delta pluses, those partial positives, and those delta minuses, those partial negatives. So in one molecule of chlorine, iodine bonded to chlorine, we can see the iodine is going to be partially positive and the chlorine is going to be partially negative. Well, if we have a nearby molecule of iodine bonded to chlorine, just kind of flipping it around, you see chlorine bonded to iodine, and we see a partial positive on the iodine side and a partial negative on the chlorine side. So what's going to happen is you're going to get an attraction between the positive end of one molecule and the negative end of a nearby molecule. And that's that attractive force that we're looking, kind of highlighting this in green. The positive end of one molecule is attracted to the negative end of the neighboring molecule. Same thing, the negative chlorine is going to be attracted to the partially positive iodine of that neighboring molecule. There's kind of another geometric way this can happen. You see this on the right-hand part of the screen. Again, a iodine bonded to chlorine, a partial positive on the iodine, partial negative on the chlorine. A neighboring molecule, iodine is going to be bonded to chlorine again, partial positive delta plus on the iodine, partial negative on the chlorine. And again, what you're going to see that I'm highlighting in green right now is that attractive force between the partially positive iodine and that partially negative chlorine. So you get an attractive force between two molecules. The partially positive end of one molecule is attracted to the partially negative end of a neighboring molecule. Now that you've seen how dipole-dipole works, we can talk about hydrogen bonding. So this is a misleading name. It's probably the worst term thing in all of chemistry. It's not an actual bond. Bonds, like we've talked about for Lewis structures, are intramolecular. That's not what we have here. Hydrogen bonding or hydrogen bonds are an intermolecular attractive force. What they really are a special strong dipole-dipole interaction. And this occurs when you have hydrogen directly bonded to a very, very electronegative element like nitrogen, oxygen, or fluorine. So here we're going to show this with two different water molecules. So the water molecule on the left, we can see oxygen is much more electronegative than the hydrogen. That means we're going to have a delta minus set up on the oxygen, a partial negative charge on the oxygen. Meanwhile, on the hydrogens being less electronegative, each hydrogen is going to have that delta plus, that partial positive charge. If we look at a neighboring water molecule on the right, again, that oxygen is more electronegative than the hydrogen. That means the oxygen will have that partial negative charge, that delta minus. The hydrogens, less electronegative, will have that partial positive charge. So again, we have this set up. Oxygen is more electronegative. We're going to see our delta minus, our partial negatives on the oxygen. And then we're going to see our partial positives on the hydrogen. What this hydrogen bond actually is it's the same thing as the dipole-dipole interaction. It just gives it a separate name because it's especially strong. It's much stronger than an ordinary dipole-dipole. So it's given a new name. But it really works the same way. Kind of what I'm highlighting in green now, the negative oxygen, the partial negative on one molecule is attracted to the partial positive on a neighboring molecule, just like we saw before with the dipole-dipole. We're just giving it a new name because it's a special case. It's much, much, much stronger than a normal dipole, so we give it its own category. Our last type of intermolecular force that we want to look at are the dispersion forces. And our dispersion forces are our weakest intermolecular force. Turns out all molecules have dispersion forces, but the ones we want to focus on are the nonpolar compounds, because so far we haven't talked about any intermolecular force that would work for nonpolar compounds. And this works from what we would call an induced dipole moment. So the diagram on the left, what ends up happening is the electrons in an atom or a molecule are in constant motion, constant kind of random motion. And the figure all the way on the left shows kind of a symmetrical distribution of the electrons. That's what you're seeing on the left. Very evenly and randomly distributed, very symmetrical. But being electrons are constantly in motion, there may be a small instant in time where there may be an unsymmetrical distribution. This is what you're seeing on the right-hand portion, kind of highlighted in blue. Imagine in an instant in time, they're not evenly distributed. Just from their random motions, that could happen. Well, at this moment that we would be looking at, kind of that's highlighted in blue, at that moment, you have a dipole moment set up. You have a partially positive end and a partially negative end. It's not permanent. It's very fleeting. If we would look at a different snapshot in time, it may look completely reversed. Right now we see more electrons on the right-hand side of the molecule for a partially negative side, and the left-hand side being partially positive. Well, if we look again at a different instant time, it could be reversed. We might have more electrons on the left-hand side than the right-hand side. And that's over the average of it, it may look like a symmetrical distribution, but in small moments of time, it will be unsymmetrical. And as a result of that, we can have these weak intermolecular forces. So what happens is this idea of what we call an induced dipole moment. In an induced dipole moment, this is kind of showing what happens on the right-hand side of the screen now, is what happens is the molecule in pink has this unsymmetrical distribution. There's more electrons on the left-hand side. Well, what that's going to do is that's going to induce or force a change into a neighboring molecule. The purple molecule, even if it started out as symmetrically distributed, based upon what's happening in the pink molecule, as soon as that unsymmetrical distribution happens in the pink molecule, I'm going to get a positive end and a negative end, partial, very, very tiny, tiny, tiny partial positives, partial negatives. Well, that partial positive end on the pink molecule, that's going to force the electrons in that purple molecule to flow to the left-hand side of that purple molecule. What happened in atom A, that pink one, forced a change in molecule B. Now these are very, very short-lived, very, very temporary, but it gives a small amount of intermolecular force that actually helps keep these molecules near each other, such that even these nonpolar compounds can still be liquids and solids potentially because of these very, very weak dispersion forces that just come about from kind of that random nature of the electron. At certain times, you're going to get an unsymmetrical distribution, and that's going to kind of cause a chain reaction in neighboring molecules. So you get very, 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 very tiny partial temporary positives and negatives that can actually be used to keep these molecules in close proximity to each other.